What's up, Neptune Nation? This is Patrick, and I'm here with Justin, one of the engineers here at Neptune and Ecotech. And today, we're going to talk about the heaters that we dissected.
Cool.
Thanks for coming, Justin.
Sure.
So, we figured we'd start off with the first heater that we dissected, and that's the titanium heater. I was really surprised about what I ended up seeing on the inside of this.
Mm-hmm.
I took an angle grinder to it, which I thought was going to show maybe some epoxy and kind of a heating element inside of that. And I was really surprised when the first thing that happened is I loaded the heater into the vise and I hear glass cracking. I wouldn't have thought there'd be glass inside of a titanium heater. What do you think? What gives? Why do you think they'd put glass in there?
Flying a little blind here, but quite frankly, it looks like it's just a standard glass heater that's armored with a piece of titanium rod around it.
Yeah, it could be. So let's take a look. I can show some cuts here of what was actually happening. We have a picture of as we pried open the titanium, what I was looking at on the inside. When we were hitting this thing with the angle grinder, it started sparking and then it started spitting out dust because we hit the ceramic and it really destroyed the insides. But this is what's left here. So you've got the titanium shell. There were plastic bits on the inside, and then here's a piece of the glass, and you can tell it fits right here inside on the outside of the plastic, right? So that piece is just kind of floating there. And I don't think the glass went all the way up, but it's really tough to tell in the rubble here. Yeah.
Well, I think what you can see, right, is that the plastic is actually a shroud that sits around and protects the winding, right? So the heat generating mechanism is basically sheltered by this during assembly, and then the glass is acting as a thermal conduction to the titanium. And then you have a temperature regulator to make sure that the device doesn't overheat in the event that it's dry.
Right. Which is an interesting point because I did run these dry and we took the thermal camera and looked at where the heat was being generated and how hot it is. So 80 degrees Celsius is this temperature regulator. So that's surprising because that coil, which is, what kind of wire do you think this is? Nichrome?
Nichrome.
Yeah. It's a wire that's wrapped around the ceramic, which I assume is going to give it some heat capacity, right? Because the ceramic's going to heat up a little bit more slowly. It's going to retain some more of that heat.
Yeah, it's going to give it a buffer, right? So it's not going to overheat in one localized area. It'll allow it to spread out.
Yeah, allow that heat from the wire to kind of dissipate. And then I assume that this plastic is right on the outside of the wire?
Seemingly. Right? If it's not, then it's not. Then you've got an air gap, and you're not going to make good thermal conduction to the rest of the
and this
housing.
thing is not potted, right? So you can tell it's open. Kind of there's air inside of it, and then you're creating this seal here with the gasket, and then you've also got epoxy potting.
Mm-hmm.
So this is very well regarded as a strong heater. This is a BRS heater, and we met the folks in Germany that create this heater, and it's very well regarded. So, anything else that we found interesting here? I think what next we'll kind of put on the screen the heat pattern. So we took this heater, we suspended it above a body of water, and we let it heat up. And here I'll put on the screen what this thing actually looked like. And I was very surprised to see that the external temperature got over 266 Fahrenheit. And it was, continuing to rise once we got to that number, which is curious because this I guess this is a solid state material that would stop allowing current to flow once it hits a certain temperature.
Solid state, I think that's a PTC.
Yeah.
Which is just, it expands as it heats up, and as it expands, it stops conducting electricity, and it cools off, and it begins conducting electricity again. One thing that you can tell is that if you sort of put yourself where these parts are going to be during assembly, it's kind of just floating inside this housing,
Yeah.
right? Like it's not in contact necessarily, at least in this embodiment. Maybe it is in one that hasn't been angle ground into oblivion, but regardless, this isn't making necessarily good contact with this outside housing. So,
Yeah, so it's just floating there in the air.
right.
Which makes sense because when you look at the image, the thermal image of the that the camera's collecting, the hottest point is down below where, 2/3 of the way down the heater, right on top of the ceramic and the coils and that localized heating. Now, because it's titanium, I would imagine you're getting good thermal conductivity through that
Certainly should hope.
on the outside,
Yeah.
but within the short time period that we were allowing this to heat up, we didn't see that whole thing become red hot. And then during the video, we lowered it down, we unplugged it, we lowered it down, and nothing really happened. It just warmed the water.
Fair. Well, that's what you want, right?
Right.
No drama, I think.
Yeah.
I'm curious, did you see it get red hot?
No.
Yeah,
No.
okay.
It was only looked red hot in the thermal
camera,
yeah.
sure.
Yeah.
That makes sense.
So the second heater that we dissected was the Hydor Jolly. So this is a plastic heater. It's a much lower wattage. I think it was 25 watts. And so it's really designed for smaller tanks. And I was curious to see what ended up being the structure on the inside of this. And you can tell this is a potted epoxy inside of a plastic shell. And as we were cutting through this, I kept trying to use a bandsaw, and it kept stopping. I was hitting something that was so hard, the bandsaw wasn't touching it.
Yep.
Clearly, ceramic, right? And so as I was shaving more and more off of this thing and getting closer to whatever was stopping it on the inside, I eventually had to hit it with the belt sander to really just shave off the last bit of plastic. It's a triangular or a square shape.
It looks like it's an off-the-shelf resistor. You've got some markings here, which show it's actually 10 watts. It's hard to make out too much of it, but I would venture that this is probably an off-the-shelf component from a typical either a heat dissipating resistor, something you might use in motor control. As you slow the motor down, that energy has to often go somewhere, and so you'll use elements like this in those type of assemblies to dissipate and absorb that excess energy. In this case, there's probably some additional either passive or active circuitry up here that is just controlling how much power is flowing to this device.
I think you're right about the circuitry. There is an LED that lit up when this thing's on, although I don't believe it has a temperature controller built into it. Now, when you look at this, it was odd to me because the ceramic seems to be only on 3 sides, and then there's the metal rod.
That's
in
normal.
the center.
So normally,
and
if
the
you
epoxy was coming down,
those are
kind
typically
of filling
potted.
that.
They're going to be potted separately. So they're going to be a
So this
ceramic U channel
Okay.
that has its own element in it, and then is potted with a ceramic filler or a ceramic.
Yeah, it does.
Doped filler.
You can kind of see that because it's white,
Yep.
the filler there, and then the green potting is on the outside. Very interesting. Well, let's take a look at the thermal camera. So as we were heating this guy up, I was pretty surprised. It does show there was 2 areas where it kind of heated. So maybe there's 2 of these 10-watt ceramic heaters wired in parallel, right? Or series, I guess it doesn't matter.
It does because R 2R versus 1/R plus 1/R.
Well, and it does say, right, it's going to heat the temperature of the aquarium. Maybe it's just designed to stay on all the time.
Yeah, I suspect it either does that or it sits there and it self-regulates its own temperature. But it does. You're right. It doesn't say. It just says.
I think it just stays on would be my guess, because otherwise there would be some sort of switch or setting. Oh,
Nice.
maybe we should check the manual. Look,
you
there's
can camouflage
decals.
it.
That's cool. So we dropped this into the tank after it was hanging there for a while, and unsurprisingly,
Did it turn itself
not a big
off?
reaction. I unplugged it.
Oh. It says it will turn itself off if it gets into a dry state.
Well, I only let these things run for about 5 minutes each, and then I dimped them. but it was really interesting. It will burn you. Like either the plastic, the glass, or the ceramic. We don't actually know how hot the glass heater and the titanium heater got.
Yep.
Because it just blew it off the chart. All right, so this is actually the most interesting one that I wanted to pick your brain on. So this is the Eheim Jaeger heater, and this is one of the really most well-respected, longest-lived products on the market.
They've been making that same heater since before I was born.
And with good reason. This thing is reliable. It stood the test of time. And I was pretty interested to see what was on the inside here. So clearly you've got your wire coil, probably nichrome like we were talking, and you're connecting a circuit, and there's a little bit of a plastic or a glass cylinder here that allows for heat capacity and the spreading of the heat like we discussed on the titanium heater. But what's going on here, Justin? What is this little glass bulb there?
So often these glass heaters will have a low intensity indicator, not an LED, but sort of a different type of illumination device that will tell you visually when the heater's on or off. So you can look at it and see if it's being powered or not. You can see your thermostat is actually built in here. It's a bimetallic strip, and then you're just, as you turn this, you're moving a screw inside of it, which is causing it to flex at a different point. One of the things I think is most interesting about this heater as compared to the others is that the heating element is really far away from the seal. And so you're not putting stress on the glass. I say it's glass, it might be some other.
Well, let's pull that up. Let's pull up the thermal image here. You can tell the bottom quarter of this thing is the only part that's hot while it's in air.
Right, which is, and that's going to be true in water too. So that says a lot for the longevity of a device like this, because everything that could fail disastrously is sort of protected just through a distance and then this air gap here. So while it looks really simple on the outside and it hasn't changed a lot over the years, it's really designed very well.
Well, I want to come back to the heating element, or the switch rather, with the bimetallic. But one thing that I've noticed on many of the heaters is that they have this minimum water level kind of setting here. And a lot of times you'll see some heaters on the market say that you can submerge the top of it, because the Achilles heel is this interface where you're sealing it. Right. You're either using epoxy generally, and you're creating that seal. And the thermal cycling, if you're allowing that heat to travel up to that seal, that's going to break down that seal over time. The more cycles that you put into it is creating a mechanical instability. Also, I think the reason that they suggest to have this outside of the water is that you're also preventing the water from interacting with the potting material, which I would assume would be harder on it over time.
There are potting materials that will break down in seawater. You would hope that what they're using there is going to be resistant to that. But it does say fully submergible, and that this is your minimum water level. And I think they're really saying that because they're relying on the temperature regulation of the water to minimize the amount of expansion and contraction that's occurring between the unique materials, right? So the plastic, the borosilicate glass, the epoxy, all three of those expand and contract at a different rate as the temperature changes. And so that actually serves to pull them apart or push them together depending on the conditions. So trying to keep everything as stable as possible is really what leads to that longevity.
In one of the early videos, we talk about different heater placement techniques, and a lot of them do show having the heater on the bottom of the tank, or on the sidewall of the tank. What really matters is that you've got enough water flow across the heater.
Sure.
You're not putting it in a compartment in your sump.
It's too small, right?
Where it's too small. I was actually a violator of that recently. I just moved my heaters into a larger compartment of my sump. And actually, I have two. I spread them out so that there's two different chambers being heated now, rather than two heaters in one small chamber, which we'll go into hopefully a little bit of the lessons learned on my side on that heater
Sounds
placement.
like a future video.
just foreshadowing, just setting myself up here, right?
Right.
So you said bimetallic metal. So I want to dive in a little bit into that. And if we look very closely, I mean, I can see certainly that copper colored kind of flat sheet here. And then you've got your, I don't know, it almost looks like a silver connector coming down, and it's creating a contact point. And as we spin this screw here, it is pushing and pulling and creating more of a gap. So with a bimetallic metal, what's happening is that one of the materials is expanding and contracting
Faster.
more strongly, with a greater degree of physical change than the other material, causing it to flex. Now, I recently learned this is how a lot of old school
Thermostats. Yeah, in your home.
worked.
Yep.
Or even thermometers, really. You have them with the coil, and then they attach the needle to the end of a long
right.
coil.
Yep.
So I think
A lot of high temperature, like oven thermostats or oven thermometers will work.
thermometers, yeah. So this is definitely very interesting, and I think it's a very reliable way to govern whether or not the heater's on or off. I do think that you will need to make sure you're calibrating your heater if you've got this methodology, because it is a physical parameter. You're not really using a microcontroller or measuring something directly with
Right.
electronics, so it's a little bit harder to calibrate, I would imagine.
It might be, but I mean, and sort of in the Neptune world, as an example, a methodology that I would probably employ would be to set it to a few degrees higher than what I actually want the target temperature of my aquarium to be, and then I would actually use an external temperature controller to more closely monitor and set the temperature.
Yeah, I think there's kind of two philosophies, and I'm not sure which one is the most robust, but you can either try to set this so you're triggering the thermostat inside of your heater to go on and off in however wide of a cycle it allows due to the material. And then you use your apex as a backup to that.
As a stopgap. Just shut it off.
Or flip it, right? Which would give you more control on when it turns on and off and creating that cycling of the heat inside of your tank.
Right.
So if you have an opinion on which methodology is more robust, please leave it in the comments. I'd be curious to hear. If you can put a finer point on some of these ideas, we'd love to hear what you think. If you're enjoying this content, please give us a like and a subscribe, and we'll keep bringing you along on our reefing journey.